The last speaker of this session is Dr. Avcı. His topic is stability analysis of YBCO, Bicrystal, Josephson, Junction, and the DC-SQUID, depending on the fabrication process. Professor Avcı, please.
Thank you for introducing me, and special thanks to the organizers. So I'm going to talk about the squids, so fabrication of high thesis squids today. Well, so my talk is going to be mostly about the stability analysis of YBCO devices, well actually especially the Josephson junctions. So as you know that the YBCO thin film itself and the YBCO devices, any type of devices made by the YBCO thin films, well, they are not stable, and they are not reliable in time. So they are, so every time when you use it, so after every thermal cycle, so they are losing their superconducting properties, and that's why there is no, well, still there is no any reliable or reproducible parameter set established so far. So that's why we are, well, the motivation of our group is to get reliable process parameters for the YBCO devices. And how can we get the Josephson junctions without any degradation of the parameters? And how can we fabricate the squid without any degradation of the squid signal parameters or noise levels? So I'm going to talk about two different types of squids that we have already designed these. So the one of them is only single squid. Well, it contains only single squid connected to the pickup loop. Well, it's called the directly coupled squid. And the other one, well, it includes the same type of squid with the first one, but it contains multi-junctions and multi-squids. So both of them are working almost similar types, almost similar way. So, well, the most important thing, I think, is the thin film structure for the Josephson junctions. Well, if we are talking about the high TC devices. So, well, it's very important to improve the thin film quality. And so that's why we are using, well, we have used a lot of different parameters in our lab by using the magnetron sputtering system. And we got these parameters, as you can see from the so the process parameters. So we are using base pressure down to 10 to minus 7 millibar and 1 nanometer per minute deposition rate, and then some 80 degrees or 780 centigrade degrees temperature, substrate temperature. So the argon pressure, oxygen pressure, and the post-annealing. So these are actually our standard parameters and optimized values. So with these optimized values, we got this type of thin films. Well, it's highly CX oriented and very nicely transition. So the TC is around 90 Kelvin with a very narrow transition width. Well, we can say that it's much lower than 0.5 Kelvin. And so, well, the thickness is about 200 nanometers. Well, for the optimization of the Josephson junction, that first of all, we have to design the type of the Josephson junction. That the width of the Josephson junction is a very important parameter, and the strip line is another important parameter. So this is the last Josephson junction designed with the YBCO. And we are using 3, 4, and 5 micrometer width junctions with the 50 micrometer strip line. So we are using one single junction in order to get the critical current values of the single junction, and then we are connecting the serial multi-junctions and in order to improve the critical current. So for the patterning, we are using standard UV lithography and chemical etching. And this is our, this is the schematic of our testing equipment. Well, of course, we are measuring the junctions parameters and the squid signals inside the mu metal shield. So these are the parameters. Well, we have discussed about the deposition rate of the YBCO thin films. Well, of course, these junctions are the bicrystal Josephson junctions. So that's why the deposition rate of the thin films are very important, because the film formation just along the bicrystal line is very dependent on the thin film growth rate. So as you can see, the growth rate is increasing, then you can get the decreasing value, critical value of the Josephson junctions. So we optimize these values at 1 nanometer per minute. And so this is our single squid, well, including the optimized values Josephson junctions. And this is, of course, our design parameters. So before fabricating the squid, you have to get the design parameters in order to get the layout. So geometric inductance levels and kinetic inductance, so some pickup loop area and effective area, so and so forth. So, well, this is our best quiz that we have ever get the, well, so in the literature, maybe you can find some levels of about 100 or something like 300 microvolts, single squid VSPP. But here we got 100 microvolts, and this is one of the best results in the literature maybe, so for the YBCO bicrystal junctions. And the second one, maybe we can get, so the reliability and operation time enhancement. So in order to improve the stability of the junctions during the time, well, so we applied 2 different layers. So the one of them might be the YBCO layer. So this is going to be the amorphous YBCO layer. And you can deposit the amorphous YBCO layer by using the room temperature deposition, because you have to protect the junctions from the temperature. And then the another one might be the STO, the strontium titanium oxide layer. So this is the dielectric layer, and it's going to be actually behaving a protective layer, so the very strong protective layer for the junctions. So we have applied for both of them, but actually we are still trying to improve the parameters for the STO layer development, but the amorphous YBCO layer has already worked. So the results can be seen here. So the first one, as you can see, after the cycles, well, for example, after 15 cycles, we can get the degradation from the noise performance of the squeeze. After 30 cycles, it goes worst. So then, after we applied the protection layer with the amorphous YBCO, so you can see this one is almost the same after almost 30 cycles. So this is what we are now applying for our DC-SQUID fabrication. And the future motivation, so we have to get some new projects for working squids with the ND-like systems. For example, our future projects is to implement a reliable squid with an ND-like system. So, and there is an ongoing project for the squid, scanning squid microscope right now. And so another future plans, well, is to developing the squids on a silicon wafer. So that's another problem, because the YBCO thin film is very difficult to deposit on the silicon wafer. And then maybe we can get some collaborations in order to improve the squids on the silicon wafers and then implement for the NCG or MRI-like applications. So thank you very much.
So, any questions, please?
Is 1 nanometer per minute the lowest growth rate that you have studied, and is there a reason why that should be the limit when 1 nanometer per minute growth rate?
Well, actually,
isn't that too high?
Well, that's our limit. Well, as I mentioned in the beginning, well, there is no any standard parameters for the YBCO thin film fabrication. I mean, there are, for example, with the PLD systems, well, people are using 20 nanometer per minute, for example. So we have used 3 nanometers per minute, 5 nanometers per minute, even 0.5 nanometers per minute. But we got the best results with the 1 nanometer per minute. And it's very critical, but it depends on the system. And it also depends on the target material itself, because every target material has its own unique parameters. And that's why we are not getting the standard deposition rate. Or, well, I can say that we cannot use the single temperature. For example, we are using 870 centigrade degrees, but sometimes we are using 800, sometimes 720. Well, all of them are working. But, well, these are all the optimized parameters for our systems, of course.
Have you looked into making arrays of squids?
I'm sorry.
Have you looked into making arrays of squids? Not single squids, but arrays?
Well, actually, no.
Because that could be one of the most interesting applications.
Yes.
Even with spreads in junctions, SQUIDs or superconducting quantum interference filters, if you can make a number of junctions in an array.
Yeah, I mean, well, we have a lot of different objectives. So, well, we can just start with the multi-squids, yes, and then multi-junctions, and then, well, switching from the squids then to the digital squids maybe, and then we can, yeah.
Well, digital squid is a little bit of a stretch, but
yeah,
if you can just make an array of squids with different loop sizes, that could be interesting to see as an absolute magnetic field detector.
Yeah.
Thank you.
Thank you.
Sorry, did you measure the critical current of your thin films, YBCO thin films that fabricated?
Critical current of the junctions?
No. Critical current of the thin films you fabricated before making a squid on the YBCO film.
But as you know that the thin films, well, all the thin films that we are using, so the substrate that we are using have the 1 centimeter by 1 centimeter size. So the YBCO thin films will have mega ampere per centimeter square, right? So the current density. So that's why in order to be able to measure the critical current, we have to make the patterning on it. So we are using 4 or 5 micrometer patterns, and then we are measuring the critical currents. So the critical currents of the thin films, well, that's not the thing that we are dealing with. So we are dealing with the critical currents of the junctions. And that's why we are measuring the currents of the junctions, and the optimized value is now about 40 microamperes.
And another question, sorry. About the squeeze, do their properties decay over time or decrease over time? Because the problem with YBCO is they lose oxygen.
Yeah, the problems of YBCO. Well, I mean, in time, so even in the room temperature environment, so the YBCO, well, thin film properties can degrade. So that's why you have to keep in liquid nitrogen or in a vacuum environment and so on and forth. So that's why we are trying to protect the device from the environment. So even, well, you don't need to use any vacuum type of system.
Thank you very much.
Yeah, thanks.
Any other question? Please.
About energy sensitivity of squid. Energy sensitivity.
Energy sensitivity. Well, actually, I'm not working with the energy sensitivity, so that's why. But if you ask that the field sensitivity,
energy sensitivity.
Yeah.
Energy.
Well, no.
good limit is quantum limit at the level of Planck constant. And all people firstly calculate energy sensitivity.
Yeah.
How much, how many.
No, I don't have any information about it.
No problem. Oh.
Questions? Okay, so let's thank the speaker again.